with the silver team. We're the spray booth pressure station. A little outline of what I'm going to go through today is a little bit of system background. We'll move on to my SSOC plot and step function. First, our laboratory simulates a spray paint booth that's located in Dunlap, Tennessee. The booths are pressurized by a blower which runs off a variable speed motor. The exhaust gases are filtered before leaving the room to help the environment. As you can see, this is a model of our system. It has 3 booths which are in their own separate room, and each room has its own filter. It has a pressure transmitter, pressure recording control, 2 remotely actuated control valves that are located at V1 and V2, and a motor drive. Our input and output. Our input is percent motor power, and our output is the pressure of the booth, which is in centimeters of H2O. It's a sample time response plot. As you can see, this one's for 80% input, and it was ran for 90 seconds. This is our steady state operating curve. Our operational output and input range is from 25 to 90. Theory about the step function. Dead time is the lag between the controller and the system over a period of time. The gain tells us how much output changes per unit change of input, and the time constant tau, and it takes 6 tau for a system to become steady. It's a sample step function plot. As you can see, it was ran for 60 seconds. And the change in input was after 5 seconds, and it was negative 20%. Sample gain plot. First, we found our change in input, which I've already said was negative 20%. Our change in C, our output was 13 centimeters of H2O. Whenever you divide the output, change in output over input, our gain was 0.65 centimeters of H2O per percent. Sample dead time plot. First, we drew the slanted line and where it meets this bottom line right here. Drew a line down, and our dead time was 0.4 seconds. Sample time constant plot. We multiplied 0.632 by the change in output to get 8.2 centimeters of H2O per percent, and drew that line across, and then where the slanted line met that line, we drew a line down, giving us our time constant of 0.5 seconds. Our overall system results. Operational input range is from 25% to 90. Operational output range is from 8 to 32 centimeters of H2O. After 9 tests, our average gain was 0.72 centimeters of H2O per percent. Our average dead time was 0.5 seconds, and our average time constant was 2 seconds. The gain and time constant both increased as the input was increased. In conclusion, all the objectives of the labs were met. We studied the input and output time responses. We determined the characteristics of our steady state operating curve, and we observed the steady state gain, lag time, and time constant. Are there any questions?